What is insertion versus removal in trees? Insertion means you're going to be adding a value into the tree while maintaining your BST order. Maintaining BST order, and you're going to add to the bottom. You're not going to change the structure yet. So your BST rule is left subtree less than node, less than right subtree. So let's say you had 50 as your node and you want to insert the following things. Well, let's just do like this. Let's insert the following in order. So let's do insert 50, insert 30, insert 70, and insert 20. How's this gonna go? Insert 20. So you're gonna have something that looks like this. You have it starts off with 50, like this, and then you're gonna go this way. You have 30, and then you are gonna have 70 here. Then you're gonna have your 20 over here all the way in this corner. So what you do with insertion, it always goes down until it finds a null. So that's why in your code you always have if the root is equal to null, you're gonna have something that says return your new node val. Now what about when you have deletion, aka removal? So this is gonna be harder because you have 3 cases. So when you have case 1, this is when you have a leaf node. When you have a leaf node, you're just able to delete it. So it's easy. So like, let's say we have remove 20, and this was what we have, 50, 30, 70, and 20. Then you would just get rid of 20 right there. You just delete it because it's all the way at the bottom, so nothing's gonna really affect it. Now, what do we do when you have a second case where you have one child on the node? So let's say you had your tree here, 50, 30, 70, 20, so this for future. So let's say we want to remove 30, right? So then if you remove 30, you have to code it so that you replace the node that you remove with its child. So by, let's pretend 70 is not here, or we can say 70 is here, so it's 50. So it takes the place of it basically. Now what about when you have case 3 and you have 2 children? So this means you replace the node with your in order successor. What does this mean? The in order successor is the smallest node in your right subtree. So let's have something where we remove 50. So if we have 50, 20, 30, let's say 40 is here, let's say 60 here, let's say 70, and then 60 over here, and then let's say you have 80 over here. So what do we do? Your successor right now is gonna be, after 50 is 60. So then you're gonna take 60 and you're gonna replace it here and you're gonna delete it. So what the result's gonna be is you have 60 up here, by to that 60, and then it looks like this. This is because of simple recursion, because you have to know you have to move that up. So insertion, you're wanting to figure out what does the tree look like afterwards, what the tree becomes. So, yeah. And also going back to an example like this, your Q output is not always going to equal to your insertion order. So only if you have a perfectly balanced tree, then your insertion order is going to be root, level 1, level 2. So that means that your level order is equal to it. So the Q traversal is printed in the same order. But usually they're not going to be the same. Because what if you have something like this? So let's look, this is our implementation here. In our implementation, if you have an insert of the numbers 50, 30, 20, 40, 70, 60, 80, your binary search tree will look like this. So you first have 50, then you have 30, then you have 20, then you have 40, then you have 70, then you have 60, you have 80. Now if you run Q, the order is going to be 50, 30, 70, 20, 40, 60, 80. So your output is going to be 50, 30, 70, 20, 40, 60, 80. But your insertion was this. So they're actually different in this case. So that's why they're not the same. So it's only the same if it was a perfectly balanced tree like in this example. So in this example, this is our insertion order, and then this is our output. It's not like a stack, but it's just like read it like this. So you have like 50, 30, 70, 70, 20, 20, 40, 40, 60, 60, 80, 80. That's because it's a perfectly binary tree. Perfectly balanced tree.